Hey everyone, ready for another deep dive? Today we're going to be talking about something pretty amazing, something called the principle of least action.
The principle of least action.
It's this idea, and this is going to sound crazy, but it's this idea that there might be just one underlying principle that governs, well, pretty much all of physics.
That's right.
So that means everything from planets orbiting stars to apples falling from trees, maybe even to how light behaves, all guided by a single rule.
It's a pretty wild thought, right?
It is, and it all starts with a pretty simple question too.
A deceptively simple question.
So how did this whole principle of least action thing even come about?
Well, it actually emerged from a challenge posed way back in the 17th century by a mathematician named Johann Bernoulli.
Oh, Bernoulli, yeah, I've heard of him.
Yeah, a brilliant guy. Maybe a little bit of a showman, too.
What do you mean?
Well, he loved to challenge other mathematicians, especially the big names. He even targeted Isaac Newton with this particular challenge.
Oh, wow, so this was like a mathematical duel of sorts.
You could say that. The challenge was called the problem of fastest descent. Imagine you have a ramp, any shape you want, and you want to get an object from point A at the top to point B at the bottom as quickly as possible. The question is, what shape does that ramp need to be?
Hmm. Well, my first instinct would be to say a straight line, shortest distance between 2 points and all that. But I have a feeling it's not that simple.
You're right, it's not that simple at all.
Yeah.
Even Galileo, the famous astronomer and physicist, thought the fastest path would be a circular arc.
Oh, interesting.
Yeah, but Bernoulli knew there was something more to it. He realized that curving the ramp downwards at the beginning could allow the object to pick up speed more quickly, so it's a trade-off. A longer path, but with greater speed.
Ah, okay, I see. So it's about finding that perfect balance between distance and speed to minimize the overall travel time.
Exactly, but finding that perfect shape turned out to be surprisingly tricky.
I bet. So, what did Newton have to say about this challenge?
Well, Newton, despite being semi-retired from the world of science at the time, couldn't resist a good puzzle.
Yeah, I can imagine.
He received Bernoulli's challenge and, get this, solved it in a single night.
Wow, classic Newton.
I know, right? Apparently, he stayed up all night working on it. Meanwhile, it took Bernoulli 2 weeks to come up with his solution.
Oh, wow. So score one for Newton.
Definitely. But while Newton found a solution, Bernoulli's approach ended up being even more groundbreaking because it led to something much bigger.
Really? How so?
Well, Bernoulli found inspiration in a completely different field, optics, the study of light.
Wait, optics. What does light have to do with objects sliding down ramps?
That's the amazing part. Bernoulli connected this problem of motion to the way light behaves. See, for a long time, people believed that light always traveled in the shortest path possible.
Yeah, that makes sense.
That idea works great for reflection, like how light bounces off a mirror, shortest path.
Right.
But when it comes to refraction, like when light bends as it passes from air to water.
Right. Like that classic broken pencil in a glass of water illusion.
Exactly. That bending means light clearly isn't taking the shortest path in those cases.
So if it's not always the shortest path, then what is it?
Well, this is where another brilliant mind enters the picture, Pierre de Fermat. He was a lawyer, actually, but he loved math and spent a lot of his free time tackling tough problems. And Fermat realized that while light might not travel the shortest distance, it does always take the path that takes the least amount of time.
Oh, okay. So it's not just about distance, it's about minimizing the travel time.
Exactly. That's his famous principle of least time. And it beautifully explains why light bends when it enters a different medium. It's all about getting from point A to point B as quickly as possible.
I'm starting to see how this all ties together, but how did Bernoulli use this to solve his ramp problem?
Okay, so picture this. Bernoulli imagined light traveling through a medium where its speed increased as it went downhill, kind of like a ball rolling down a ramp. He applied Fermat's principle of least time, and with a little help from calculus, he found that the fastest path for an object sliding down a ramp wasn't a circle.
Okay.
It was a shape called a cycloid.
A cycloid? What's that?
A cycloid is the curve traced by a point on the edge of a rolling wheel.
Wow, that's a surprisingly elegant solution.
Isn't it?
It's kind of amazing to think that a problem about ramps could be solved by thinking about the way light behaves.
It is, and it hinted at something much deeper, a more universal principle at play.
Okay, so this is where the principle of least action comes in, right?
You got it. Bernoulli's solution was just the beginning. It sparked a whole new way of looking at physics, and that's where our next fascinating character, Maupertuis, comes into the picture. Maupertuis was totally captivated by this idea that maybe a single principle could govern both light and the motion of objects. He was a student of Bernoulli.
Oh, I see.
And so he really took this idea and ran with it. He looked at Fermat's principle of least time, and he started thinking, why should time be the only thing nature cares about?
Yeah, it does make you wonder if there's something, I don't know, maybe even more fundamental going on, right?
Right, like time's a big deal, but maybe it's just part of a bigger picture.
Exactly.
And that's when Maupertuis had this pretty bold idea. He introduced this concept called action.
Action.
Yeah. But action in physics, it's not the easiest thing to wrap your head around. Think of it as a measure of like how much effort is involved in making something happen.
Okay, more action equals more effort. I think I need an example. Can you give me a real-world example of action?
Sure. Imagine you're pushing a heavy box across the room. The farther you push it, the faster you push it, and the heavier that box is, the greater the action involved.
Okay, so like nature's always looking for the easiest way to do things, the path of least resistance.
Exactly. That's basically what Maupertuis was saying. He proposed that out of all the possible ways something could happen, nature will always, always choose the path that requires the least amount of action. Like it's some kind of universal efficiency rule.
Wow, that's a big claim.
Yeah.
But okay, I'm curious now. How do you actually calculate this action thing? What goes into it?
Well, the way Maupertuis defined action was as mass times velocity times distance.
Okay.
So going back to that box you're pushing, the box's mass multiplied by how fast you're pushing it, multiplied by how far it travels across the room, that gives you the action.
Okay, I think I'm starting to get it. So like when I throw a ball up in the air, it's not just following any random arc, it's actually following the path of least action.
Exactly. Pretty mind-blowing when you think about it.
It is.
Yeah.
So how did other scientists react to this bold new idea? Did they immediately embrace it?
Not quite.
Oh.
Maupertuis unfortunately got a lot of pushback for his principle. Some people accused him of stealing the idea from others. Some people just dismissed it completely. Wow.
And then there were some who, well, they went out of their way to make fun of him. There was this guy, Voltaire, the famous writer.
Yeah, I know who Voltaire is.
Well, he actually wrote a whole pamphlet mocking Maupertuis and his principle.
Ouch. What was the problem? Was there something wrong with Maupertuis's principle?
Well, to be fair to the critics, Maupertuis, he didn't exactly have all of the mathematical details worked out. He presented this really grand idea, but he didn't really have rock-solid proof to back it up.
Ah, so it was more of a brilliant insight that still needed some rigorous mathematical support.
Yeah, you could say that. And he also kind of overlooked some really important conditions that are necessary for the principle to work properly. But luckily for Maupertuis's legacy, and I guess for physics in general, two real giants of math came along, Leonhard Euler and Joseph Louis Lagrange.
Euler and Lagrange. Oh, yeah, I remember those names from physics class. Although, to be honest, it's been a while. Can you remind me what they did exactly? Oh, you're in for a treat. These two were amazing. First, you've got Euler. He was a huge supporter of Maupertuis's principle. He saw the potential, and he really set out to refine the math behind it.
So Euler basically took this somewhat vague idea and made it mathematically precise.
That's a good way to put it. He got rid of those clunky sums that Maupertuis had used and replaced them with integrals, which are much, much better for describing motion that changes smoothly over time.
Okay.
And in doing that, Euler realized something crucial that Maupertuis missed. The principle of least action only really works if the total energy of the system stays constant. It's a really key condition.
So Euler added that missing piece of the puzzle. And what about Lagrange? What did he contribute?
Lagrange, well, he was a prodigy, a brilliant mathematician, even when he was young. And he and Euler actually ended up collaborating. They were both passionate about making this principle work. And get this, just 1 year after Maupertuis passed away, Lagrange managed to produce a general mathematical proof for the principle of least action. He totally vindicated Maupertuis's original idea.
That's amazing. That's like a tribute to the guy. So we've got these two brilliant minds taking this kind of rough diamond of an idea and polishing it into a powerful tool. But I gotta be honest, I remember this principle seeming pretty complex back in my physics days. I mean, why even bother with all of this when we have Newton's laws of motion? Isn't ESMA a lot simpler?
It's a fair question. A lot of people wonder that. You see, Newton's laws are great. They work really well in a lot of situations, but they rely on forces, which are these things called vectors. And vectors, they can get kind of messy to work with, especially when you're dealing with more complicated systems.
Oh yeah, I remember vectors, those things with both magnitude and direction.
Exactly. They can be a headache. But Euler and Lagrange, they figured out that you could use the principle of least action to derive equations of motion using energy instead of force. And energy, luckily, is a scalar, just a number. So the math becomes a lot cleaner, a lot easier to work with.
Ah, so it's like viewing the same problem from a different, maybe more elegant perspective.
Yeah, a more efficient way of looking at things. They introduced this concept called the Lagrangian, which is basically the kinetic energy of the system minus its potential energy.
Lagrangian,
Yeah.
right, right. I vaguely remember that, but I'm still a little fuzzy on how it actually simplifies things. Can you walk me through it?
Sure. So they came up with this equation called the Euler-Lagrange equation, which essentially tells you how the system changes over time based on this thing, the Lagrangian. And the beauty of it is that it works no matter what coordinate system you're using, which makes it incredibly versatile.
So it's like a universal tool that can handle all sorts of physics problems, even really complicated ones.
Exactly. Imagine you're trying to describe the motion of a double pendulum, those two pendulums linked together, swinging all over the place.
Yeah, that sounds pretty chaotic.
Oh, it is. If you try to do that with Newton's laws and forces, it would be a nightmare. But if you use the Lagrangian and the Euler-Lagrange equation, it becomes much more manageable.
Wow, I'm really starting to see the power of this principle. It's come a long way from just, figuring out the quickest path down a ramp.
It really has, and its reach extends far beyond just classical mechanics, the physics of everyday objects. It pops up in all kinds of unexpected places in physics, like in quantum mechanics, which governs the world at the atomic and subatomic level.
Seriously, that's incredible.
Right. It's almost as if this principle is baked into the very fabric of the universe itself.
That's wild. But before we go any further, can we just clarify something about the name? You mentioned earlier that it's not always about the least action. Is that right?
You're right. That's a really important point. The principle is more accurately called the principle of stationary action. It's not always about finding the absolute minimum action. It's really about finding those points where the action doesn't change much if you make small variations.
So it's kind of like finding a point of balance where the action is stable.
Exactly. Imagine a ball at the very bottom of a valley.
Okay.
It's not going to move unless you give it a good push, right?
Right.
That's kind of similar to what's going on here. It could be a minimum, like that valley, but it could also be a maximum or even something called a saddle point. The important thing is that it's a point where the action is stationary.
Okay, so it's technically the principle of stationary action, but everyone just calls it the principle of least action because it's, well, a bit easier to say.
Exactly. It's one of those things where the less precise name just kind of stuck. It just goes to show you that even in science, things aren't always as simple as they seem.
Wow, we've covered so much ground today. I mean, from sliding objects down ramps to the bending of light and this concept of action and all these brilliant mathematicians, it's pretty mind-blowing to see how all of these things come together under this one principle.
Yeah, it really highlights the power of human curiosity, right? We started with this seemingly simple question about finding the fastest path down a ramp, and it's led us to this deep truth about the way the universe works.
It's amazing, and it makes you think, right? If nature's constantly optimizing for something, always seeking out this path of least action, what does that say about reality itself?
It's a profound question, and it's one that physicists and philosophers have been grappling with for centuries.
Yeah,
I mean, is it just a mathematical quirk, or is there something deeper going on? Is there some underlying order, some purpose maybe in the
that's
universe?
a lot to ponder.
It is. And, so far we've mostly talked about the principle of stationary action in the context of classical mechanics, the physics of everyday
Right.
objects. But it actually has a much wider reach than that. I mean, it pops up in all sorts of unexpected places in physics.
Like where?
Well, like in quantum mechanics, for example. In the early 20th century, physicists were struggling to understand how atoms behave, specifically how they emit light. Classical physics, what we've been talking about so far, predicted that atoms should radiate an infinite amount of energy at high frequencies, which we call the ultraviolet catastrophe.
The ultraviolet
Yeah,
catastrophe.
and obviously that's not happening, or we wouldn't be here to talk about it.
Right. Everything would just be, like, fried. So clearly something was missing from classical physics.
Exactly. They needed a new theory to explain what was really going on, and guess what played a key role in solving this crisis?
I'm going to guess it was the principle of stationary action.
You got it.
Yeah.
By applying this principle to the behavior of electrons within atoms, physicists were able to develop quantum mechanics, this amazing new theory that accurately describes the world at those really, really tiny scales.
So this principle that started with ramps and sliding objects, it ended up helping us understand the very building blocks of matter.
Isn't that amazing? It just shows you how a seemingly simple idea can have such profound implications.
It does, and it really is inspiring. I mean, it seems like this principle of stationary action is like a universal language that reveals some of the deepest laws governing the universe.
It's a beautiful way to put it. It really is.
So to wrap things up today, we've gone on quite a journey from that rivalry between Bernoulli and Newton to the elegant work of Euler and Lagrange.
And through it all, you've gained a real understanding of this incredibly powerful concept, the principle of stationary action. You've seen how it arose from these, well, pretty basic questions, how these brilliant minds refined it, and ultimately how it shapes our understanding of the universe on, well, on every scale.
It's been quite a deep dive, and we're going to leave you with one final and hopefully thought-provoking question.
Hmm.
If nature is constantly optimizing, always looking for that path of least action, what does that tell us about the nature of reality? Is it just a mathematical coincidence, or is there something more profound, maybe even philosophical, going on here?
Yeah.
Think about that as you go about your day, and, well, maybe you'll see the world in a whole new light. We'll be back again next time with another fascinating deep dive, ready to spark your curiosity and explore some more of the mysteries of the universe. Until then, keep exploring, keep asking questions, and never stop wondering.